So, welcome everyone. Good afternoon. My name is Ooijevaar. I'm a senior research engineer at the Strategic Research Center Flanders Make. And within Flanders Make, we do pre-competitive research to help companies to make the step towards Industry 4.0. So today, I will talk about machine upgrading 4.0. What are the challenges and what are the opportunities? So, many companies nowadays are still using machines that are maybe 10, 20 years old. These machines, they have not yet reached the end of their useful life. But yeah, they also don't fully, let's say, meet the current state of the art and state of standards in terms of sensors or functionality. So at some point, the question might come up, do we want to upgrade this machine or are we going to replace it? Well, within this talk, I would like to show you that in some cases, upgrading of an outdated machine can be an interesting solution. Reasons could be, well, first of all, it could be financially, it could be interesting to upgrade the machine. From a reliability point of view, it could be interesting. Something new doesn't mean that it is always better. Training, people are used to using the machine. They have been working with it for many years, so it requires less training. Or placement. Sometimes a machine or system is deeply integrated in a building. Then, yeah, replacing is a big challenge. And finally, of course, also environmental aspects could be a reason to upgrade a machine. But if we look to machine upgrading, there are still a few big challenges. First of all, what is the business case? And that's the most important question. And also the most challenging question. How do you determine the costs and how do you quantify the benefits or the return that you obtain? A second challenge is what to upgrade. As we can see here on the fair, on the exhibition, there are a lot of providers of technical or solutions or technology providers. Do you upgrade the electrical part, mechanical part, or do you want to do both together? It's a big challenge. The last challenge, how do you implement it? How do you connect the old with the new? But also, more from a project point of view, how do you ensure that the current production, for example, is only barely affected? That are all challenges that many people are struggling with. If we look to the types of transformations, I see 4 types of transformations. First of all, we have the electrical transformation, where you could think of, you upgrade a control unit, maybe you upgrade cabling, you want to transfer towards field bus communication. That's the first set of transformations. A second transformation, mechanical transformation, where you can think of, you maybe want to upgrade worn parts, or you think about upgrading the actuators even. A third transformation is the digital transformation. And that's the intersection where data combined with connectivity and with data analytics, for example, machine learning, deep learning, comes together. Mainly with the purpose to increase efficiency and to improve the operation of the machine. And finally, the last transformation is a conformity transformation. So how do you ensure that you meet with the current state standards in terms of machine safety in terms of machine safety? There's, for example, important to consider, if you make adjustments to your machine, who will be finally responsible for these adjustments? So in the remaining of this talk, I will mainly talk about the digital transformation. And that's when I talk about machine upgrading 4.0. So the digital transformation process consists of different steps. It starts with sensors that need to be able to measure the right properties. Then connectivity. You need to be able to access the data that is available at different locations often. But then we come to a part that is, let's say, identical for Industry 4.0. What about the visualization that gives you insight in what is happening? The understanding, why are the changes happening that you see? the prediction, what does it mean in future, or when can I expect that the change will happen? And ultimately, adaptation, meaning how can I make an automated smart decision, keeping in mind that certain things will change around my machine. Key driving technologies behind this are, well, data analytics and AI, and of course, digital twins. So these are topics where we within Flanders Make are actively working on. To give you two examples, first of all, let's say you want to make a digital transformation to be able to correlate product quality variations to process parameter variations within different process steps. So what is important in that case? Of course, that you have the right connectivity, that you're able to access the data that is distributed in different production steps of your production line, and that you actually can explore this data. A second example, if you want to add, for example, condition monitoring capabilities to your system to enable predictive maintenance, what is important in that case, first of all, that you have the right sensors, but also that you have the right methods and tools to do prediction on when, like, your machine or component will potentially fail. Well, how do we bring this all to practice? To show that, I will like introduce you to a demonstration case that we've worked on within Flanders Make. It's called a living lab, and it's focused on an industrial compressed air network in our facilities in Lommel, which is in the north of Belgium. Within Flanders Make, this compressed air network was installed about 20 years ago, and we use it basically to, well, supply compressed air to all our facilities. So we have different test labs, from simple test labs to more advanced test labs where we can test full vehicles exposed to vibrations, sort of like UV exposure, and also sort of temperature and humidity. The compressed air system here is used to, for example, regulate the humidity in the climate chambers. But it's not only that, we also use it for several other equipments throughout our facilities. Over the years, we've seen several issues have been reported. First of all, we observed quality issues in terms of the air. We saw particles, oil particles in the oil, but also maintenance issues. For example, leakage in the network, pollution, and also several other repairs. So this was for us, an indication that, hey, potentially there's here an opportunity to further improve the operation of this system. So the question that we asked ourselves was, can a gradual digital upgrade help us to improve the operation of this compressed air network? And the starting point for this analysis is basically a cost-benefit analysis. You can do this in different ways. There are different tools to do this. Well, in a simple case, it can come down to just a return on investment analysis. If you want to do it in a more advanced way, you easily go to like a life cycle costing or a total cost of ownership analysis. What is the key issue there is, of course, it takes time. The better the data you have, the better analysis you can make, the better decision you can take. But often, having information about the cost of such an installation that was installed 20 years ago, you don't know. Huh? And that's not the only thing. It's also about the hidden costs. What about the project management? What about the documentation that you still need to make? So they're all cost items that you need to take into account to have a full view on the cost that you're going to invest. Luckily, the majority of the costs are often determined by a few key items. That's not the only thing. So secondly, well, to be able to make an accurate cost-benefit analysis, it requires a commitment. Often, like, knowledge is stored somewhere in the brains of people that have worked with the system. Maybe they were involved in the purchase or in the maintenance action. So it requires often involvement of many people throughout different layers of an organization to have an accurate estimate of the cost. Especially the first time, knowing who was involved is something often not that straightforward. So what would it mean for our case? So we identified 3 main driving cost items. First of all, the purchase cost, which was quite straightforward. We could look back to our original invoices, so that was easy. For the maintenance cost, it was already a bit more difficult. We had to look in old logbooks, but that was not the only thing. We also had to talk to our facility manager, who was involved in the different inspections, but also did regular inspections himself. And that is also time that you need to take into account. Finally, we had several breakdowns over the years, where we temporarily rented a spare compressor to be able to continue with our experiments. These costs also needed to be taken into account. The big challenge, however, was to get an estimate of the energy consumption. We didn't know. Yeah. The compressor was just running there and just pressurizing the pressure tank. We didn't know exactly. So basically, we had insufficient data to come to an accurate estimate of the total costs, and so also of the final benefits. So how did we estimate the cost involved in this machine? So first of all, we had the expertise, talking to the facility manager. We had historical data, but the big unknown was the operational data. We didn't know. We didn't know how often the compressor was switching on and off. But that's a crucial element to be able to make a right decision in the end. So what we did in the first exercise, we made the first iteration of the upgrade. We basically wanted to get a better understanding of the usage of the compressed air by the end users. So we basically wanted to install sensors throughout the network to get an understanding of the usage. So what we did, we installed sensors throughout the network. This is a whole overview. For example, what we did in the bottom, it's very detailed, but you can, in the bottom, we installed flow, pressure, temperature sensors. We also installed current and voltage sensors to get an understanding of the power consumption. And we just started logging data, basically. This data was all connected to a software framework where we pushed the data through an MQTT broker to an influx database where we stored the data. Then the data was used in different services, and it was all managed by a so-called Node-RED software layer, which is a low-code programming environment. It allows you to easily connect different data sources and to set, for example, thresholds. Then we pushed this data also to a dashboard where we could visualize and see the statistics from all the different end users in our facilities over the last days and also over the last months. For example, if you look here to the consumption, we saw that we had a rather high idle consumption, and every now and then we saw a significant increase in the consumption, and that was mainly due to the operation of the climate chambers. So what did it learn us? Well, first of all, it learned us that, a big part of the costs were associated to the energy consumption, almost about 70%. But that was not the only thing. Secondly, what we observed was that we had a rather high ideal consumption. So almost the ideal consumption daily was about 30 euros a day, so 1,000 euros a month. This was mainly due to leakages somewhere hidden in the network. Secondly, we saw that we had clearly alternating periods where we needed a lot of compressed air and periods where we only need a limited amount of compressed air. So alternating periods of high demand and low demand. Well, we couldn't also just switch off the compressor in the low demand periods because there was always infrastructure that need to be kept pressurized throughout the year. But this was actually the starting point to think about what could we do in a second iteration of the upgrade. There, besides mitigating, of course, all the leakages in the network, we looked and we compared 3 different upgrade scenarios. First of all, what would happen if we just leave it as it is, no upgrade? What would happen if we would change actively the pressure presets of the compressor from a high level to a low level, depending on the demands and needs from the users? Or thirdly, what if we would add a small compressor to just serve the small daily consumption that we sometimes see? So what we did, we compared these three scenarios. We made a cost-benefit analysis tool, and we evaluated those up to 2025. Important to notice there is that, okay, there's a large uncertainty on the costs, as I already mentioned. So we didn't only kept one value into account, but we also looked to the worst case and the best case. So if we compare the three scenarios with each other, so on the left-hand side, no upgrades. The middle one, if you go to the active pressure presets, or the right-hand side, if you would go to add a small compressor, we could see that both actively upgrades would result in a reduction of the annual cost by 2025. We see that, okay, adding a small compressor would ultimately lead to a lower annual cost, but of course requires at this moment a higher investment. So we made a decision to go for this second scenario. See what could we achieve with changing the pressure presets, depending on the usage of the end users. So basically, it comes down to a second iteration of our upgrade. So in the first iteration, we added additional sensors that allowed us to get a better insight in the operational usage. That allowed us to make a more accurate cost-benefit analysis, and that allowed us to make a better decision on what upgrade is the most appropriate in this case. So as I said, for the second upgrade, the initial situation was that the compressor was always running in its high pressure preset. And we thought that we can lower that, in particular in the periods when there is no clear demand or the demand is much lower. And it would reduce the consumption because you have a lower leakage losses. So we changed the pressure presets from 8.8 to 8.3 bars to 6.5, 7.5 bars by externally interfacing with the compressor. We could use an external interface to basically activate different presets. By doing that, we evaluated the pressure preset evaluation over the last year, so between April 2021 and 2022. And it showed us that in almost 83% of the time, we could switch to a low pressure preset, which would save us, in the end, energy. So what was the final reduction in energy that we obtained? Well, mitigating leakages is quite efficient. Yeah, that's obvious. Secondly, by actively setting the pressure presets, we could achieve another 13 to 18%, depending on the consumption of the end users. Coming to the end of my talk, some key takeaways. First of all, well, defining the best upgrade scenario starts with a cost-benefit analysis. That's maybe rather obvious. But the difficult thing is, there's a large uncertainty on these numbers. And how do you get good estimates? And that requires involvement of many people in different layers of the organization. So it's more a process rather than a one-time activity or exercise that you do. Secondly, well, and don't forget the hidden costs. Then the final point, what I showed here is that following a gradual digital upgrade strategy could allow you to rather quickly get insights in the operation and usage of your machine. It could identify large cost drivers and show you what opportunities for improvement you have. And this ultimately could lead to a reduction in the operational costs or potentially enable new functionalities in your machine. Well, in the end of my talk, what I talked about now is mainly digital transformation. I didn't talk about electrical, mechanical, and conformity transformations. However, we have written a white paper about machine upgrading 4.0. If you would like to know more about these other types of transformations, or I would highly recommend you to download the white paper, either via the QR code here, or just write me an email, or visit us at the booth of Flanders Make, which is just here across the venue. With that, I come to the end of my talk, and I would like to thank you for your attention.